Hydroplaning can mean pleasure, or it can mean trouble. Hydroplaning keeps water skis on top and can lift aircraft tires off the runway. This results in extremely low friction coefficients. Aircraft tests have confirmed that braking effectiveness is generally reduced when operating on even slightly wet runways because of lubrication effects between tire and ground. However, the same aircraft tests show even greater reductions of braking effectiveness in the presence of a deep fluid, in this case slush, and it is under these conditions that tire hydroplaning becomes a serious problem. The NASA Langley Research Center has for some time conducted research on this problem, initially with a small wheel and belt arrangement, but more recently at one of its facilities called the Landing Loads Track. The test carriage at this facility can be catapulted by a water jet to speeds in excess of 100 knots. In this research program, various aircraft landing gears and aircraft tires were mounted on the test carriage and equipped with detailed instrumentation. During these studies of tire behavior, the runway conditions varied from dry to covered with 2 inches of water. The effects of slush depths from 1/2 inch to 2 inches were also investigated. It was substantiated during this research program that on wet runways, partial hydroplaning occurred at the lower speeds, and at a higher speed and under certain repeatable conditions, total hydroplaning developed and wheel rotation stopped completely. On the basis of the research, we can explain this phenomenon and offer a simplified explanation of the physical principles. On a standing tire, the only force acting is the ground reaction caused by the weight or vertical load on the tire. For a rolling tire, the situation is more complex, since ground friction, tire deformation, and tire hysteresis are involved. Let us assume that the tire is rolling freely at a fixed forward speed on a dry runway. A rolling resistance force acts in a direction opposite to the motion of the tire and produces a moment on the tire in the accelerating or spin-up direction. To maintain a constant rolling velocity, this spin-up moment must be opposed by an equal spin-down moment, which is produced by a shift of the vertical ground reaction to a position ahead of the wheel axle centerline. The introduction of deep fluid on the runway complicates the picture further, since additional drag on the tire is produced when the fluid is displaced from the wheel path. Also, as the forward speed is increased, the spray pattern thrown up by the tire changes, and a wedge of fluid penetrates the ground contact region, reducing the ground contact area and producing a hydrodynamic lift force on the tire and a condition of partial hydroplaning. As the forward speed is further increased, the spray becomes flatter, the wedge of fluid penetrates further into the ground contact region, and the hydrodynamic lift force becomes progressively greater until at some high forward speed, the hydrodynamic lift force becomes equal to the vertical load being supported by the tire. At this point, complete separation occurs between the tire and the ground. This is the condition of total hydroplaning. Under this condition, ground frictional forces causing spin-up are reduced, since large shear forces cannot be developed in a fluid, and the predominating spin-down moment tends to stop wheel rotation. With further increases in speed beyond total hydroplaning, a large reduction in fluid drag force develops because the tire rides up out of the fluid and hydroplanes along the fluid surface. Directional stability and braking effectiveness of the tire are therefore progressively reduced through partial hydroplaning conditions and nearly vanish at total hydroplaning speeds.